All right, part 2. Net change, or if you want, net change theorem. In this part, we learn how the fundamental theorem tells us how to calculate net change. Okay. Guess what? Our friend, part 2 of the fundamental theorem of calculus, essentially says this. This should become inscribed on your hearts, this thing. Okay? I sort of wrote it this way once. This should make sense, okay? We said that big F was the antiderivative or an antiderivative of what was in here, so I've written it like this, okay? The stuff in here is the derivative of that guy. Okay? That's just part 2 of the fundamental theorem. Okay? All right. This is what's cool. This is the net change. The net change in f of x, big F of x, as x goes from a to b. Okay? As x changes from a to b, that's how much big F changes by. What's this thing? That's the definite integral of the instantaneous rate of change. It's the definite integral of the instantaneous rate of change of f from a to b. Okay? So we can get the net change in something by integrating the instantaneous rate of change. Cool? Just a billion sides of the same coin. Okay, so the net displacement again. Okay, we talked about net displacement before. Now we're going to talk about it. We've seen it a few times, really. And now we're going to talk about it in the context of net change. An object moves along a straight line, so we can talk about its position as a single number. Okay, at time t in seconds, its velocity v in meters per second is given by this guy here. Find the object's net displacement from time 0 to time 2. So over the first 2 seconds. Okay, net displacement is the change in position. All right. Again, I said, what is that? That's just the signed area under the velocity time curve over the interval. But let's talk about it in terms of net change. Net displacement is the net change in position. We got a position thing? No? Okay, if, again, I call my position function p. What are we asking? We're asking how much does p change as we go from 0 to 2. Okay? What does this guy say? It says that if you want net change, all you have to do is you have to integrate the rate of change. That's it. Okay? What's the derivative of position? Velocity. It's good to see something from 10 different angles. Okay. Where's our function? Okay, our velocity was what? Cos pi t plus a half t. always check, is this guy continuous on this interval? Yes, it's continuous everywhere. So we can do our usual thing. Okay, we want an antiderivative of this thing. Again, you can break up sums and differences, and you can pull out constants. What's an antiderivative of this?
Sine.
Sine is good. Sine of?
Pi.
Sine of pi t. Divided by? Pi. Excellent, thank you. Okay, if I just had this and I took the derivative, I would get cos of pi t by chain rule times pi. So this cancels out that pi, getting us what we wanted. Okay, do this however you want. You do this in one step. Pull out the constant, whatever you want. Okay, what's an antiderivative of t? T squared over 2. Good? Okay, so an antiderivative of a half t is a half times a half t squared. So a quarter t squared. Okay, again, check. Okay, I've already talked about this guy. This guy, if we take the derivative, the 2 comes down. We get 1/2 here times t, 1/2 times t. Okay, there you go. There's your antiderivative. Evaluated 2, subtract evaluated 0. Now, unlike the last one, this one's nice. Really, really, really nice. Okay, do I want to write it out? I'll write it out. Here we go. 1 over pi sine pi times 2, 2 pi, plus 1/4 times 2 squared, minus, evaluated at 0, sine 0 times pi is just 0, plus 1/4 times 0 squared. Sine 0, 0, that's 0. Sine 2 pi is 0. All you're left with is this guy, 4 over 4, which is 1. Which again is nuts, okay? Okay, what are the units of this thing? Meters? Meters. I'll talk about that in a bit. Okay, but it's position. It should be in distance units or something like that. Okay? Change in position, displacement should be in distance units. Okay, so that is our net displacement. Okay, what does that tell us? It tells us that overall net we moved forward 1 meter. Yes, ma'am?
You're constantly reminding us to check if the function is continuous. Would we ever be put in a situation where it wasn't?
Probably not. It's possible. It would be mean to do it. Okay? Yeah, it would be mean to do it. And in some cases, if it is, you can't really repair it. So, yeah, it would be mean to do it. Put it that way. But in case I ever show you something where, I don't check that, you should be able to see that it's not good. Yeah, it'd be mean to do it. Okay, we're good? Okay, what is this thing? What did we just do? We got the definite integral of velocity from 0 to 2. Okay, what is that? That's the signed area associated with the velocity time curve from 0 to 2. Okay, so it's this area minus this area plus this area. Okay? And madly, that's 1. Okay? Okay. What else do I want to say? Okay. Over here, velocity was positive, we were moving forward. Over here, velocity was negative, we were moving backward. Over here, velocity was positive, we were moving forward. Okay? So we're doing this sort of thing. Right? And what we were talking about was the net displacement, the net change in position. Okay? So, overall, after all that stuff, where do I end up relative to where I started? That's what net displacement is. That's what net change in position is. Okay. The lesson with this kind of net change stuff is what? If you want the net cumulative effect, okay, of a varying rate of change, you integrate it. Okay? If you want the net cumulative effect of a rate of change that varies, you integrate it. That's the point. Okay? And here we talk about net displacement. Almost there. Just a few more examples. Look at this on your own time. we did this one, okay? So the net change in position is given by a definite integral with respect to time of velocity, okay? That's what we just talked about, okay? Velocity is derivative with respect to time is acceleration. So you can do the same sort of thing with velocity and acceleration, with volume and flow rate, with concentration and reaction rate, population size and population growth rate, and charge and current, okay? This thing applies to a lot of situations. I will say this just so we can wrap this thing up, okay? So it's the last thing I'm going to say, just because I want to wrap this lecture up. 20 seconds. Okay, units of this, the units of something like that are the units of f times the units of x. That's all. Okay? Look at the Riemann sum. You'll see that you're going to be multiplying things with units of x by things with units of f. Okay? Or look at the integral and think about it that way. Okay? So in the last example, we would have had what? We would have had meters per second times second, so meters. So that's where you got those units. That's the end of that, guys. All right, we'll talk about integration by substitution next time. Tutorial today. If you have any questions, come talk to me. Thank you very much.